Okay, so we were looking at graphs. We started with some basic definitions, and today I'm going to first introduce bipartite graph. It's very simple, a graph is bipartite. If you can partition the vertices into two parts, part A, part B, such that there is an edge between, uh, you know, one vertex set to other vertex set, but not between same vertex set. Okay, it's a bipartite graph. It's a very simple thing, but I'll give you the definition, examples, and so on. And so these things are quite useful uh, from the application point of view. For example, in communication, in the wireless communication scenario, or when you have to assign different frequencies to different users at the same time, so how do you assign? So basically, we kind of color them. So I'll show you what is the relationship with coloring. So it's a very interesting thing. Then I think we are going to talk about representation of graphs, adjacency list, incidence matrix, adjacency matrix, and so on. And then we are going to talk about connectivity of a graph, when a graph is connected or disconnected, and so on. After that, finally, I think not today, probably in the next lecture, we are going to talk about circuits. So Euler circuit or Hamiltonian circuit, these are two very famous problems. And I mean, all these problems are they originated in a natural settings. While studying some society problem or something, and then you sort of come up with a solution using graph theory. So it's really very easy. And as I mentioned, graph theory is very useful for different algorithms. Once the problem is converted into graph theory, then you can actually use it to solve different problems. And I'm also going to talk about isomorphism. I'll give you some examples of isomorphism of the graph today. And so after circuits, and then we can talk about trees. So then, special kind of trees, prefix code, and so on. And then we'll also going to talk about Huffman coding. How that is a very popular technique for compressing the data. Okay. So I think one more thing. I think whenever I think still some people are confused about selecting a project. So I suggest you look at any of the standard technology and look at how it works, how it uses discrete mathematics. It's such a popular thing. So it could be, for example, you look at your iPhone or mobile phone or whatever, right? And there is a video call going on. Can you find out what is the discrete mathematics behind that video call? Or, there is some sort of chatting going on, right? So how chatting is done? Social network, Facebook, LinkedIn, when you post something, what happens to the network? And actually, it's really interesting to know that all these networks has connection with chemistry. So enthalpy, entropy, those kind of things are connected to the network. Beautiful things, So you can see variety of things we can talk about. So anyway, so let me start the basic bipartite graph today. Neural, yeah, you can do anything. It doesn't matter. By the way, there is a, if you really want to look at another interesting topic is complex network. So complex networks can be used, for example, you can make algorithms for cooking. How to have great cuisine, so there are people who have studied European, countries. So Borobursky work is there, which is very important. Where actually, by studying the complex network, you can actually find out interesting things, how you can make good food. And actually, in the Indian scenario, this work was done by Ganesh Baglar, who is at IIIT Delhi, who was earlier here actually. So that is also an interesting area. So complex networks is a beautiful area. A lot of applications you can see. So related to graph theory, of course, because it is network, right? And there are different kind of properties like power law, that can also be used to study how it epidemic or pandemic like COVID is spreading, you can model that using those networks. So variety of tons of applications are possible of complex networks. You will see that whenever you are making a friend on a Facebook, there is a mathematical law behind it, right? So you need to know how it works. If someday you can talk to me about these things, we can talk for hours, but anyway, I have to start the class. So you can search on the internet as well, right? So there is no issue on that. Okay, so somebody is asking. That is okay. One has to see there is no copy paste. Topic could be same. Okay. Bipartite graph. Bipartite graph BG. So a graph G is equal to V comma E is bipartite graph if vertex set can be decomposed to two vertex set V1, V2 such that every edge in G, actually every edge in E connects a vertex in V1 and a vertex in V2. And so basically it should be something like two sets. So there will be connections like this, but there will be no connection like this between vertices, right? If there is a vertex here, there is a vertex here. This is not allowed. Okay, this is allowed. Okay, so another this is allowed, or this is allowed, right? This is allowed, but connection like this is not allowed. This is not allowed, right? So if there are certain vertex here, certain vertex here, so connections between the vertices are allowed in these two sets. Okay, edges are there, but there are no edges between same collection between the vertices, right? There is no edge. So that is a bipartite graph. Let me show you an example. V1, V2, V3. Sorry, V1, V2, V3, 4, V5 actually. So this I can say V2, V4, V6, 5, V3, V1. So you see that so as you can clearly see that, so there are edges between vertices in one set to the vertices in the other set, right? And there are no edges between same collection, right? That is a key property of bipartite graph. So as I mentioned, these are quite useful in communication channels. So as an example, C6, the cycle, is bipartite graph. K3 is not bipartite. So it is very easy to ask questions like that. Give an example of a bipartite graph of length 6. Right. So sorry, number of vertex 6, right? Or give an example of a graph which is not bipartite. These kind of questions you can always ask in exams, right? So you have to think. Okay. So now one interesting result which I would like to mention. It's a theorem. A simple graph is bipartite graph if and only if it is possible to assign one of two different colors to each vertex of the graph so that no two adjacent vertices are assigned the same color. So what does that mean? A simple graph. So basically there is no loop and all those things, right? All those kind of things are not there. It's a simple graph. Is bipartite graph. If and only if it is possible to assign two different colors on each vertex, two different colors, right, on each vertex. So one vertex you say blue, another vertex green, and so on, such that no two adjacent vertices which are connected by an edge have the same color, right? If you can do this, that means we can partition easily, right? So all those with one colors you can put it in one side basket. With different colors you can put it in another basket. So that means there is an edge between, two different baskets, but not in the same basket, right? You agree? It's a very easy thing. I think last time we have proved it. Want I can prove it. It's not a very difficult thing. So I think you assume that start coloring. Maybe if you want, I can do something. So understanding is very important here. This side. Suppose G is equal to V comma E is a bipartite simple graph, right? So then we are putting, we are actually distributing vertices of this graph into two baskets, V1 and V2, right? Such that V1 intersection V2 is empty. Okay, they are two disjoint ones. So then in that case, so basically, once we are able to do this, so what we are trying to prove actually, let me show you. So I have to prove that I am assuming that the graph is bipartite graph. So now I have to prove that I can assign these two different colors. So what I will do, I will make these two bars. So if graph is bipartite, so one collection will be V1, another collection will be V2, right? Such that there is an edge between any vertex in V1 to any vertex in V2, right? And no edge between any two vertices in V1 or any two vertices in V2, right? There is no edge like that. So one vertex set I can assign one color, another vertex set I can assign another color, right? So we are able to color it. Very simple thing, right? Got it? So assign one color in V1 and one in V2. So it is, if you look at by example, so this is a bipartite graph. So this is given to us. So I will assign these with V1, V3, V5 with blue color, and I will assign V2, V4, V6 with red color. So two different colors, right? Color assignment can be done, right? Similarly, reverse question if you ask, if this kind of color assignment is possible, how to make bipartite graph? Just put one colored things in one thing and the other colors thing in the other basket and you are done, right? It's really fairly straightforward thing. Anyway, so let me give you an example now. A, G, B, C, D, E, F. Making this graph will take some time, but anyway. A to C, there is a connection. B to C, there is a connection. F to B there is a connection. A to F, there is a connection. F to D, there is a connection. C to D, there is a connection. E to D, there is a connection. E to A, there is a connection. G to D, there is a connection. E to B, there is a connection. Okay. So the question is, this graph is given to us with vertex set A, B, C, D, E, F, G. 1, 2, 3, 4, 5, 6, right? Whatever. So now the thing is that how do we so one thing you can note, the number of edges are not even, right? That so the number of vertices in V1, V2 is need not be same. They may be different actually, right? Okay, so now I start coloring this. I have to check whether this graph is bipartite or not. So what I do, I start coloring edges, right? Start with one vertex. Say I pick up vertex A. Okay, I pick up vertex A. Assign is red color. I'm putting a circle because I cannot. I mean, anyway, it's all red. So if A is a red color, A is connected to what? G, C, E, and F. So if this is red, then this, and this will be blue, right? Right. So all other. So that means if A is assigned red, then C, E, F, and G are blue color. Okay. Now what I do, whatever is adjacent to C, E, F, and G, I assign them a red color again because I have to go further, right? If I do that, this will imply that B and D are red, right? So basically, we are able to make two sets. V1 is equal to A, B, D, and V2 is equal to C, F, and G. The red, right? So we are able to make such that we need to remember no two adjacent vertices have same color. This is the property you need to keep in mind, right? So this graph is bipartite graph because we are able to assign two different colors each vertex such that no two vertices are adjacent. So such that no two adjacent vertices are assigned same color. Okay, so we can do so. This is a graph which is bipartite. So I am going to draw another graph and I'll ask you the question whether it is bipartite or not, right? So I think, yeah, so this is red and this is red, right? So these three are red and others are blue. Take another example. A, B, A, B, C, sorry, B, D, C, F. Okay, so this graph is bipartite or not? Please check and tell me. You can start with A. Assign A as a red color, then proceed. So this is the graph. Is it a bipartite or not? Please let me know. So and when you start coloring, you will observe that there are two vertices which are adjacent and assigned the same color, right? So this is not a bipartite graph. So basically, you start with A as red. This will imply that F, E, and B are blue. That means D and C should be red. Okay. And D and C are adjacent, you know, these are adjacent, assigned the same color. So there is a problem. Okay. So now take a graph G is equal to V comma E. So this graph has vertex at V and H at E. I'm just taking H is equal to W comma F. This will be a subgraph. Subgraph of G if W is a subset of V and F is a subset of E. Right. So there is a graph G given. I am constructing a subgraph out of it. So whatever is the vertex set in G, it contains vertex set of H, and the edge set E contains the edge set of H. Right. If we can do this, then it's a subgraph. So let us take an example. A, B, C, D, E. The graph is complete graph, K5, complete graph. So I can construct a subgraph A, E, C, C. This is your H. Certainly H is a subgraph of G. Right? So from a graph, I can construct a subgraph by taking certain vertices and edges such that they are subset, the corresponding subsets of the bigger one, right? This is something easy to observe. These are the definitions anyway. W. You may say empty set. That will be trivial anyway, all the time, right? Trivial graph is always possible. Okay, now we can talk about union of two graphs. I'm always talking about simple graphs. G1, G2 are simple graphs. So G1 is V1 comma E1 and G2 is V2 comma E2. Union graph G1 union Z2, I can say V1 union V2 and E1 union E2. So basically take a graph G1 as A, B, C, D, A, B, C, D, E. And another graph G2 is A, B, C, and D. So the union will be A, B, C, D, just union. So the corresponding vertex sets are union and the edges sets are union, right? So combination of both. This is not there, please. I mean, I think that's somehow A, B, C, D, E, F. Okay? This is the union. I think those competitive programming lovers, for them now, something interesting is coming. They should know what I'm going to tell now. Is representation of a graph. How will you tell a computer about a graph? How will you encode? Suppose I ask you to program something. How will you program? So for that, you require some kind of representation of the graph. All these vertex and edges and their connections, you need to encode them in the form of graph. So we require some sort of structure. I mean, which is very useful. I think these things you will also learn in Professor V. Sunita and Priyanka Singh course, right? But anyway, I have to mention here representation of the graph. Suppose G is a graph without multiple edges, right? So we have A, A, C, D, E. This is a graph A, B, C, D, E. So I have to represent in a computer, right? So one way is we prepare what is known as adjacency list. I make a list of vertex and adjacent vertices. See, all these things in graph theory that you study are common sense. There is no concrete mathematics. It's all common sense, right? A, it is adjacent to B, C, and E. D, what is adjacent to A? C adjacent to A, D, and E. D adjacent to C and E. E adjacent to A, C, and D. Right? Each vertex adjacent to what? You can write. So it's adjacency list of the representation of the graph, right? इसमें क्या mathematics? It's a common sense, right? You can just write a way to represent everything. You can also represent directed graph when there is a direction actually. Okay? So there you can represent basically initial vertex and terminal vertex, right? And then you can represent it, right? Something easy. Now this is pretty interesting. Adjacency matrices. Whenever there are matrices, beautiful things can be done. So look at this example. A, B, C, D. So vertex set is A, B, C, and D. I can represent it by a matrix A is equal to A, B, C, and D. A, B, C, and D. So A is connected to itself. I mean, there is no loop, right? So simple anyway. A is connected to B, yes. C, yes. D, yes. B is connected to 1. So 1, 0. 1, 1, 0, 0. 1, 0. This is a adjacency matrix. It's binary matrix from a graph, right? So if it is connected, I will put 1. If it is not connected, I will put 0. So we get a matrix. अब अगर मैट्रिक्स आ गई, आइगन वैल्यू आ गया, आइगन वेक्टर आ गया, ब्यूटीफुल कहानी you can construct right out of these things. Moreover, this is binary matrix Z2. So, right, so a lot of interesting things can be done. Similarly, somebody can give you a matrix and ask you construct the graph. You can do that, right? Just write down the column numbers as a vertex and whatever row number, and then you just draw it, right? Something very easy. So the question is, which representation should you use, adjacency list or adjacency matrix? When the graph is simple graph and sparse mean number of non-zero entries are very few. Most of them are zeros. Then adjacency list is a very preferred method of. So basically, depending upon the structure of the graph you are handling, you can choose one of the way. Because as you can clearly see that with respect to matrix, you require a lot more arrays to store and so on, right? So all this overhead will be there whatever method you prefer to operate. Okay. Next representation is incidence matrix. Again, I'm going to write a graph. If I would have used slides, probably it would be easy thing anyway. V1, V2, V3, 4, V5. This H is E1. This H is this is not there, please. I don't know this kind of 6, 5. E2, E3, E4. E1, E2, E3, E4, E5, yes. And E6, all 6 edges. This is undirected graph. So what I'm going to do, I make a matrix known as incidence matrix. I write down edges E1, E2, E3, E4, E5, E6. And what is number 1, 2, 3, 4, 5. 1, 1, 0, 0, 0, 0. If it is incident, I am putting 1, otherwise it is 0. 0, 0, 1, 1, 0, 1, 0, 0, 0, 0, 1, 1, 1, 0, 1, 0, 0, 0, 0, 1, 0, 1, 1, 0. So incidence matrix. So I look at vertex V1, right? And there are 2 edges incident to it, E1, E2. So there will be 1 there, otherwise it is 0, right? Like that, we can construct this matrix. This is the incidence matrix representation of the graph. Again, there is a matrix. Beautiful things can be done out of the matrix, right? So okay. Now I am going to give you the most interesting concept in graph theory, is known as isomorphism of 2 graphs. 2 graphs are isomorphic if there is a one-to-one correspondence between the vertex set and the edge set such that their, the adjacency relationship is preserved. Understand what that means? If two vertex are connected here in this graph, their corresponding images are connected here. That should be there, right? Then the two graphs are isomorphic. Okay. So let me show you an example. Let's start with an example so that you understand what I am saying. Look at this graph G and H. There are two graphs. U1, U2, sorry, U3, U4. Oh, this is really bad. Again, G equal to V and E. H is equal to W and F. One, U2, 3. And here it is V1, V2, V3, V4. So if you observe these two graphs, are they isomorphic? The question is, are they isomorphic? The question that I asked. You can clearly see that if I take this and fold it like this will be same, right? I take this portion and rotate it like this only. That portion is fixed, right? It's kind of twist. I'm just taking a twist of these two part, right? We'll get the same graph, right? So this twisting business is nothing but a map actually, which I am operating, right? So basically I can precisely define. So these two graphs are isomorphic because there is so we say that G and H are isomorphic. So because there is a twist here which we can be performed. So because there is a function, more formally, there is a function such that f of u1 is equal to v1, f of u2 is equal to v4, f of u3 is equal to v3, and f of u4 equal to v2. This function f is one-to-one and onto. So this map is one-to-one and onto map between two graphs such that if two vertex are adjacent to each other in one graph, their corresponding images are adjacent in the other graph, right? Via this map. So these two graphs are isomorphic. So basically, while classifying the graphs, this is very important thing that as you remember in the last class, I asked up to vertex n, how many graphs are possible? So if n is 2, how many graphs? N is 3, how many graphs? N is 4, how many graphs? No matter how good competitive programmer you are, I am damn sure if you can produce me a program which can classify graphs up to n is equal to 15, I will give him a party, right? Great competitive programmers. So you have to classify all the graphs and up to n is equal to 15, say, or 16. This data has been generated. There is a Australian Open University. There is a professor who has written a program, Naughty, N-A-U-T-Y, Naughty program for classifying graphs. Very useful. As a data structure person, yeah, I mean, because see, many things can be molded into graphs, and the basic problem of classification comes quite often. And whenever you are doing classification of graphs, basically you are trying to check whether the graphs are isomorphic or not. These graphs are nothing but interesting data which you can use for any kind of applications. Okay, so it turns out that this Naughty program can do this classification. It's a good algorithm what they have come up with. So, but you see, up to n is equal to 10 or 11, the data is available. For 12, 13, 14, I think there are some partial attempts, but the full attempt is a challenging thing. Such a simple problem, classifying graphs up to certain n. How many graphs are there up to length n? So, any idea how many graphs will be there? Maybe I can show you. I have a I think this is nutty traces base. So you can see that there are certain data is available. Bernardi Mackay, he has done a lot of work. Somewhere data might be available to. So there is a complete manual how to use. So I invite you, by the way, to look at this page and look at the program and see if you can classify. I mean, you can look at the data. I think somewhere the data was given. I've used this long time ago, but fractal graph isomorphism problem, something you see, this is there. Maybe some data might be given here. I am not sure. Let me check. This is all beautiful mathematics. So I think data is not given there. Somewhere the link might be given. Anyway, you can find it out. It is search. How many graphs are there? So if you just search, types of graphs, subtotal points are there. Okay. So this data you can get it from that Bernardi Mackay homepage. I hope that is okay. Okay, so this is all about isomorphism of graphs. Let me do a couple of more examples. B, A, C, D, E. This is a graph G, this is a graph H. You can see that number of vertex is 5 and number of edges is 6 in both the graphs, right? My question is, are these two graphs isomorphic? Any idea? Any great thinker? Whether these two graphs are isomorphic? Yeah, you have to observe why. No? I mean, there are many observations. So for example, look at vertex E. It has degree 1 and this has degree 3. So they cannot be isomorphic anyway. This answer is easy, right? Finding that they are not isomorphic is easy. Whether they are isomorphic, you have to find, that is the kind of, so finding a map is a difficult thing, right? Anyway. Sometime even the degree sequence is same. Means degree sequence means each vertex has certain degree. So you can find for a given graph, there is a degree sequence means, degree of each vertex in one graph is same thing as degree of each vertex in other graph. Then telling whether the graphs are isomorphic or not is another interesting question too. I think इससे ज़्यादा नहीं करना, बस हो गया, right? By the way, कोई अभी हो तो नहीं पा रही है, बट मैं एक प्रश्न सोच रहा था, देखता हूँ तुम में से कौन करता है. Alpha times an plus beta times an minus 1 is equal to So you know the quiz question, right? The next quiz. I can just change 4, 5, 6, 3. Solve this simple recurrence relation and you are gone. And I'm sure you will not find on Google, right? Huh? So I think just for fun, try it. And I think so next class we'll talk about connectivity, then circuits. Very much.